So the derivative of the function is telling you where the function is changing or how the function is changing at an instant. Now when you're looking to try and find the points where the derivative is 0, that's going to be where the tangent line is horizontal. So a place like this is where the tangent line would be horizontal, or down here, or here. Those are where you'd have horizontal tangent lines, and the value of the derivative function at those points is going to be 0. 0 there, 0 there, 0 here, 0 here. So you should have 4 points on your little plot where the derivative is 0. Now, it's a little harder to see the next one, but places where the derivative is 1 or -1. And just to give you a little bit of reference here, this is a line with a slope of 1. So imagine a tangent line having this kind of slope. So you want something where the function looks like it's parallel to that slope. So where would those points be? Or on the flip side, where would those points be if the tangent line had a slope of -1? And this is an example of something with a slope of -1. So let's see if we can't fill in some of those points as well. So can anyone see a place where the function looks like it might have a slope of a tangent line equal to 1? Yes?
At 0?
Yeah, at 0. At 0, looks like it's a 1. The tangent line would be right there. Looks like it has a slope of 1. Perfect. Where's another point like that? Come here. 2 pi, nice. Although 2 pi is a little bit beyond our graph, but yeah, 2 pi. Negative 2 pi. Negative 2 pi would be another one. Good.
Pi and -pi.
What's happening at pi and negative pi? Are we getting slope of 1 or something different? Slope of -1. So -1 here. Let's see. -1 here. So, okay, and you're starting to fill out a little bit of a function. You're starting to get enough to maybe trace it. And, you know, this isn't going to look as good as it will on Desmos, but something like that. And let's take a look at it on Desmos rather than look at this. So on Desmos, here's your places where the function has a derivative of 1 or -1, and bam. All right, so this is left over from a previous semester. Let me take that out. What does this function look like? Let me shut off the sine function. What does that graph look like? The one in blue.
Cosine function.
Cosine function. So it's reasonable to expect or see that the derivative of sine is cosine. Yay. So the good news for you is that you get to memorize all these things. Yeehaw. So here's 6 new derivative rules for you. Derivative of sine is cosine, but it doesn't work the other way around, does it? Derivative of cosine is not sine. Oh, that's kind of annoying. Derivative of cosine is negative sine. Yeah, sorry. In fact, if you look through these, derivative of tangent is secant squared. Derivative of cosecant is cosecant, cotangent. But there's a negative in them. In fact, there's a negative in 3 of these. So right here, and right here. And I want to give you a little mnemonic for these negatives because they're easy to forget and they cost you points. So I don't want you to lose those points. If it starts with a C, its derivative gets a negative, right? You've got cosecant, cotangent, and cosine. All of those start with a C, and all of them have negatives in their derivative. So, okay, great. So keep that in mind as you're keeping this memorized. We're going to pair this up with stuff like this and practice our product rule and quotient rule, that kind of thing as we go through this section. But for starters, you've got this little thing here. You might want to keep that handy as we look at things like example A, where we've got h of theta is theta squared sine of theta. Now, I remember as a first-year calculus student being annoyed by the product rule. Because I'd look at stuff like this and like, really, you want to call this a separate function? And it's not like a want to thing, but it's a have to thing. We're going to have to regard this as an f, and this is a g, and we're going to have to apply the product rule because you're multiplying two functions. Even if this was just a theta, you'd still have to multiply by, or you still have to apply the product rule. So let's start out here, f and g. F is theta squared, g is sine of theta. And then I'm going to need f prime and g prime. What's f prime and g prime going to be for this one? Omar? 2 theta, good.
And then the sine would be
Nice. And cosine of theta. Nice. It's 2 theta to the first power, but we're not going to write that. I'm not interested in seeing that. Thanks, Omar. So h prime of theta is going to be f prime times g plus g prime times f. So let's fill that in. It's just really kind of a cross product of these things. This times this plus this times this. So it's going to be 2 theta sine of theta plus cosine of theta times theta squared. I want to put that theta squared out in front. When you put that theta squared behind this, there's a tendency for people to want to multiply the thetas together and get theta cubed. That would be wrong. You can't do that. So there you go. And that's it. There's our derivative. Nothing really spectacular going on there, but there's our derivative. Are we okay with that first one? Thumbs up? Yes?
How does the f prime become 2 theta?
So we're just treating this like we would any polynomial term. You take the 2 out in front. It multiplies really a 1, 2 times 1, and then subtract 1 from the exponent. So it's not really written, but it's understood that there's a 1 here. So, but we're not going to write that because it tends to look like a prime, and yeah, it's just not so good. Antonio?
On the exam, can we substitute with the theta with like x or like a regular letter, but at the end switch it back? Will you points or?
If you really wanted to do that, I guess I'd be okay as long as you write it in the right notation at the end. But hopefully you get comfortable differentiating in any variable, all right? The rules are still the same. Anything else on example A? Appreciate the questions. Thank you. Let's try example B. So we've got y equals 2x over 7 minus tangent of x. What rule do you think I'm going to have to apply here? Quotient rule. All right, so I think you guys liked u and v, so let me go back to that. I'm just going to write it very simply. U over v, it's going to be v squared, and then v times u prime minus u times v prime. Square the denominator, then the denominator times the derivative of the numerator, and the numerator times the derivative of the denominator. So let's figure out our u and our v. U is going to be 2x. V is going to be 7 minus tangent of x. Give yourself a second to figure out u prime and v prime. See if you can't figure those out. Feel free to look back at your little sheet here. Remind yourselves what the derivative of the tangent is. Didn't say here this morning? Oh, there you are. Cool, cool. Help me out. What's the derivative of the first one? 2. Nice. Thank you. And let's see. Arlie here this morning? Yeah. Okay, cool. Arlie, how about the derivative of the second one? All right, derivative tangent is a secant squared x. Good. There's also that minus out in front of it, which doesn't go away exactly. So it's just going to be minus secant squared. Wonderful. Thank you both. So let's try and put this together in this form. Now, when you differentiate both sides, you're differentiating with respect to x. I'm going to use some different notation here. Let's call this dy by dx. You could also call it y prime. That's fine. But I'll use dy by dx here just to mix it up a little bit. We're going to start by squaring the denominator. 7 minus tangent of x squared. And if you notice, you use the denominator twice before you ever differentiate it. So we're going to use the denominator again. That's going to be 7 minus tangent of x times the derivative of the numerator, which is 2, minus the numerator, which is 2x, times the derivative of the denominator, which Arlie gave us was minus secant squared. Okay. We can clean this up a little bit. It's not going to clean up tremendously, and I'm not going to bother to square out the denominator. Let's just leave that as minus 7 minus tangent of x squared. I'll distribute the 2 and get 14 minus 2 tangent of x. And then here, I'm going to distribute the negative 2x. So that whole thing there has to distribute itself to that. So there's going to be a plus 2x times secant squared of x. And that's about it. There's no real simplification I can do beyond that. I mean, I suppose if I really, really wanted to do something, I could factor out a greatest common factor of a 2, but that's not going to do a whole lot for us. So, nice. Nice. Good with that one? Yeah, thumbs up on that one? All right, thank you so much. Alex, how you doing there? Doing all right? Cool. Okay, let's keep it rolling. Now, there's a link for this stuff on D2L. It's on the announcements page if you wanted to check that out and follow along. But let's move on down to example C here. So, example C. This is certainly something you should expect on your exam this Wednesday, is to find the equation of a tangent line. So, our function is f of x equals 3e to the x times cosine of x. And we want to find the equation of the tangent line at x equals 0. Now, I know that the function actually gives you the point itself. I hope and I trust that you can figure out, if x is 0, what the y coordinate is. So the y coordinate would be f of 0. What's f of 0 going to give me? Yeah, it's going to give you 3. So e to the 0 is 1, cosine of 0 is 1, times 3 is 3. So you should be able to get that point for yourself. WebAssign seems to always give you that point. I will ask that you find that point. So I'm just giving you a heads up on that. We need two things to find the equation of a line. What are those two things? Slope, good, and a
Tangent line.
we're trying to find the tangent line. What two things do we need to find the equation of it?
Slope intercept, a point.
Yeah, we need a slope and a point, right? We've got our point, so our point is 0, 3. The slope, how do you find the slope of the tangent line? What's going to tell us the slope of the tangent line there?
Find f prime.
Yeah, we're going to find f prime. So that's going to be f prime at 0. So we're going to need to find the derivative then, because it's the derivative that tells you the slope of the tangent line. All right, so where's Alvin this morning? No, Alvin. All right. David's here. David, What rule am I going to have to use to find the derivative here? Product rule. All right. I'm going to call this a u and a v. The product rule, if I write it with u and v, is going to be u prime v plus v prime u. Okay, good. So let's write these down. U is 3e to the x. V is cosine of x. Now you can put that 3 with either one of these. It doesn't really matter. I just put it with the 3e to the x, u prime, and v prime. Nice. Thanks, David. Ashley, what are we looking at for u prime? We kind of look past the derivative of the 3, look past the constant. What's the derivative of e to the x? E to the x. All right. How about the derivative of cosine of x? Negative sine of x. So let's put these two things together. I want u prime times v plus v prime times u. So f prime of x is going to be 3e to the x times cosine of x plus v prime times u, negative sine of x, times 3e to the x. Now, a lot of times, all you're asked to do is calculate the derivative. If you were asked to calculate the derivative for WebAssign, you could type that in and you'd get the right answer. But we're actually going to have to do some work with this. And moving forward, you're going to have to do even more work. So my suggestion is that we get used to cleaning these things up a little bit now. Is there anything I can do to clean this up a little bit?
Multiply 3x by the cosine and negative sine x.
Yeah, nice. So basically factor out the 3e to the x. 3e to the x is a greatest common factor here. So thank you. Yes, we're going to factor that out. When I do, that leaves behind cosine of x minus sine of x. That's just a little tidier expression to have to evaluate. Now remind me, why did I go through all this effort to get the derivative here? What good does that do me? Rebecca? Yeah, find the slope of the tangent line. So I'll call this m subtangent. Just remind you, we're finding the slope of the tangent line is going to be f prime at 0. So we're going to plug in a nice big 0 here into our derivative function. 3e to the 0, cosine of 0 minus sine of 0. And how about another one up there? What's the sine of 0? I know it's going all the way back to trig. It's like, oh, yeah. Sine of 0 is 0. Cosine of 0 is 1. E to the 0 is also 1. So we get 3 times 1 minus 0. That's a times here. Overall, I'm going to get a 3. So looking good. I've got my point and I've got my slope. Those are the two things that I need to find the equation of a line. There's a couple ways you can do this. There's your m. But these are the things that I needed right here. There and there. Let's put them together. If you haven't done this in a while, one way to do it is this function. So reminder, y minus y1 equals m times x minus x1. And we've got our y1, x1, and our slope. So it's going to be y minus 3 equals 3 times x minus 0. Or in other words, y equals 3x plus 3. Nice. Very nice. I don't know. Would you say we've done a fair amount of work on this problem?
Yep.
So this problem's worth, a reasonable number of points, maybe 6 or 7 point problem. So it'd be nice if we could check our work somehow. And you can. Let's take a look at the graphs here. So that'd be this one here. Here's your function. Here's our point of tangency that we're looking for. Okay, looking good on that. Let's take a look at the graph of the derivative and see if it makes sense. One of the things that makes sense to me is that this function is increasing until we get to this point. What's the slope of the tangent line at that point? 0. And guess what? The derivative at that point is also 0. So that looks good. Then the function starts decreasing, and guess what? Then the derivative is negative. So that all makes sense. Let me hide this graph real quick. Let's throw in the graph of the tangent line, and bam, look at that. The tangent line just touches really nicely the graph right at that one point. It's said to osculate, which is a fancy way, it comes from a Latin word, means to kiss, about as romantic as math gets. So don't be sending mathgrams to your sweetheart on Valentine's Day. But in any case, it looks great. I mean, that's exactly what we expected of our tangent lines. It's going to be really tightly hugging the graph, especially at the point of tangency. So, looks good. You can double check yourself on these things pretty nicely. Okay, let's try another example. Is there any question on that one? Okay. Let's move on down to example D. Do you want to do a little side journey first? Let's do a little side journey before we do example D. Let's calculate the derivative of this one. So, call it bonus. D by dx of cosine of x over sine of x. Okay. Let's see. Angelo, what rule am I going to have to use to differentiate this? I'll give you a couple. Quotient rule, product rule, or power rule? Yeah, quotient rule. All right. So this is a quotient. We can regard this is my u and this is my v. So u equals cosine of x, v equals sine of x, and I want u prime and v prime. So, D'Angelo, help me out with a couple derivatives. U prime and v prime.
U prime would end up being negative sine of x,
Nice.
and sine of x would just be cosine of x.
Nice. Okay, let's keep going. Let's actually work through this. So remember, u over v. Let's make that a v prime. Start out by squaring the denominator. Use the denominator again times the derivative of the numerator, and then the numerator times the derivative of the denominator. So a lot going on here. So the derivative, d by dx of cosine of x over sine of x. I'm going to start by squaring the denominator. Sine of x squared. And then it's going to be sine of x times minus sine of x minus cosine of x times cosine of x. Okay. Please resist the temptation to cancel out the signs like this here. You can't do that. But we can clean this up a little bit. Does anyone see or suggest anything we can do to clean this up? What's sine times sine? What's another way I can write that? Sine squared. Good. So minus sine squared of x minus cosine squared of x over sine squared of x. That's looking better. I think we'll keep going though. Alex, is there anything I can do to clean up the numerator a little bit? We'll factor out a negative from both of this, so that leaves you with sine squared of x plus cosine squared of x. And a couple of people have already gone a little bit past that, because you recognize this part right here. Sine squared plus cosine squared, what's that equal to? 1. So it's negative 1 over sine squared of x. Ah, well done. Which is negative cosecant squared of x. Nice. But does anyone see a much faster way we could have done this? I mean, real nice light speed jump in that. Yeah.
Isn't cosine over sine just cotangent?
Yeah. So that's d by dx of the cotangent of x. And I just gave you a handout. It said derivative of cotangent of x is minus cosecant squared. So, wow, minus cosecant squared of x. At least it matches, right? So we got that going for ourselves, which is nice.
So basically you can do it both ways.
Yeah, yeah, you don't have to do this the long way if you catch that. So, yeah. No, if you do that, great. I mean, if you do it with a quotient rule, hey, that's good practice too. And notice I only did one of these kind of from scratch. You can prove all of these, you know, this one, these 4 here, the same way, you know, with the tangent rule or secant, etc. Secant, you're going to regard this as 1 over the cosine and then use the quotient rule. All right, and then you just got to be clever using some simplification, but it works. All right, we now resume our regularly scheduled lecture. Go back to example D here. Example D. So we've got y equals 6x sine of x. And we want to find the point of tangency at x equal pi over 2. And y is 3 pi. I'm not going to bother you trying to make you plug in the pi over 2. I trust that you can. So in order to find the equation of the tangent line, we're going to need to find dy by dx. Now I'm going to try to start moving away from always having to write down the f and the g or the u and the v. I'm going to call that f and g. And I'm going to need f prime g plus g prime f. Now f is going to be the 6 and the x. It's going to be that whole term out in front. So I'll give you a minute to try and fill that in. See what you can come up with it. If you're watching this at home later, give yourself that same opportunity. See if you can't fill that in.
It's all right.
if you get the derivative, try and find the slope of the tangent line by calculating the derivative evaluated at pi over 2.
I just,
Oh, okay.
I was on the other page.
Okay. Okay. Just for good measure. All right, so the derivative of the first, what's the derivative of 6x? 6. So it's going to be 6 times sine of x plus derivative of the second. Derivative of sine of x is cosine of x. Good, we started out with that, times 6x. Now, I prefer to put that 6x out in front here so that I don't mistake these and try and multiply them together somehow. Or, in fact, there's a greatest common factor here, right? 6. Let's take that out in front. So it's going to be 6 times sine of x. I'll move that x here, plus x cosine of x. Looking good there. And now the slope of the tangent line. So m sub tangent is going to be, let's see, the function evaluated, or the derivative evaluated at pi over 2. So it's going to be 6 times sine of pi over 2 plus pi over 2 times cosine of pi over 2. Now, if you're looking at that going, oh man, I just never was really good thinking in radians, that's fine. No big deal on that. Hopefully your calculator is in radian mode. Mine is. If it's not, then just hit the mode key, go down and switch it. Let's check it out here. We can do sine of pi over 2. And what are you going to get? 1. How about cosine of pi over 2? You can do the same thing there. Cosine of pi over 2. What do you got? Before I hit the key, anyone? 0. Big 0. All right. So we end up with a 1 and a 0. Now 0 times pi over 2 is still going to be 0. So what's the overall value of the derivative, the slope of the tangent line? 6. Nice. So 6 is the slope of our tangent line. We got the point pi over 2 and 3 pi. So let's see here. So it's going to be y minus y1 equals m times x minus x1. Let's plug in and solve. Y minus 3 pi equals 6 times x minus pi over 2. So it's going to be y minus 3 pi equals 6x minus 3 pi. Or how about just y equals 6x as the equation of our tangent line? How are we looking on that one?
Could you re-explain how we knew that it was pi over 2 for the sine and cosine?
How we got the values there, or?
Yeah.
We just took the sign on our calculator. Yeah, we just plugged it in. You know, if you remember these things, that's great. If you don't, hey, your calculator can help you out. One other little trick here, and I'm glad you asked, Charles, because you're not always going to get pi over 2 or pi or 3 pi over 2, those kind of points. What if you got the cosine of, say, let's do pi over 6. Cosine of pi over 6. Now that's not going to be a nice, easy number. You're going to get 0.866, etc. And you look at that going, yeah, I got nothing. And then you get real clever and you hit the math key, you hit the answer to fraction key, and it comes back with the same thing. You're like, ah. Oh. So if you're really at a loss, here's what you can do. Hit the square key. And it's going to take this number and square it. And you get something that you should recognize. What's the decimal value Or what's the fraction for 0.75?
3/4.
3/4. But remember, we squared it to get that, right? So really, what we started out with was the square root of 3/4. Square root of 3/4 is the square root of 3 over square root of 4, or better yet, the square root of 3 over 2. And that's the kind of answer you're going to need sometimes when you're trying to get an exact answer that WebAssign or I will ask for. If you're just asked for a numerical approximation, sure, you can get away with 0.8660, but you know, if you're looking for exact numbers, and oftentimes I am, then you can do stuff like that to remind yourself what these things are. All right, let's look back at this one for a second. Y equals 6x. Is there a way I can check that? We've done a lot of work. Is there a way I can look back at this and say, you know, I want to check that? What could we do? Yeah, thank you, D'Angelo. Graph it. Let's take a look at the graph and see how that plays out. So let me shut off these here and turn on this one. So let's see, and we wanted our point here, which is this one. And where is that? How come I'm not seeing our point? Pi over 2. Oh, that's because I'm not there yet. There we go. There's our point. Let's take a look at our tangent line, which is going to be this one right here. And yeah, looking good. All right. Just that nice little touch of the function to the by the tangent line. Looking good. Looking real good. So if you made a mistake somehow and maybe you subtracted things and you had like a minus 6 pi here or something like that, then yeah, that'd be a bummer. Let's take a look at y equals 6x. Maybe you made a mistake and subtracted minus 6 pi. Notice that your tangent line, yeah, it's got the right slope, but it's not touching this point at the right spot. So at that point you realize, oh, there's a mistake someplace, and you can have a chance to go back and fix it. Beautiful. Beautiful. All right, let's flip it over. Keep rolling. Let's take a look at example E. Now, example E is going to give you a chance to realize that, you know, some of those trig identities that you played around with, the manipulating those things, actually do help out. Let's start with finding the derivative just kind of as is. So we've got f of x equal tangent of x minus 1 over the secant of x. Antonio, what rule am I going to have to use to differentiate this?
The quotient.
Quotient rule. So it's going to be another u over v kind of thing. All right, good. Let's see. U equals tangent of x minus 1. V equals secant of x. I need u prime and v prime. So, Amir, what's u prime and v prime going to look like here? And feel free to look at your sheet. This is still new. All right, secant squared of x. Nice. The 1 disappears when we take its derivative. Good. And then, oddly enough, secant has as a derivative, yeah, secant x times tangent of x. Nice. Thank you, sir. Yes?
Why'd the 1 go away?
You can think of 1 as being, say, x to the 0 is 1. And if you're to differentiate this, you get 0 times x to the negative 1, but 0 times anything is going to be 0. Or a different way to think of that, Stephen, is the derivative measures the slope of the tangent line, which is the rate of change. Now, the graph of y equals 1 really isn't changing, right? So the derivative of something that's not changing is going to be 0 because it represents that there's no change. All right. Appreciate that.
What is the name for that process that we just did there?
This one or
The we learned it in 3.1, but it's AXN and then you take the
oh, so the derivative it's a derivative of a polynomial term. So if you have f of x is ax to the n, then the derivative f prime is going to be n times ax to the n minus 1. So two things happen. The n comes down and multiplies out in front, and then in the exponent you subtract 1. So those two things happen when you differentiate a polynomial type term. Now that only works for polynomial terms. Unfortunately, a lot of people want to extend it to things where e to the 3x. They want to differentiate it that way, and you can't. We don't know how to find the derivative of e to the 3x yet. That comes when we learn the chain rule. But this only works for polynomial type terms. So if I had, for instance, sine of x to the 5th power, I can't just do, 5 times sine of x to the 4th power. It's not quite right. But we'll learn how to work around that with the chain rule soon enough. Great questions. Let me get back to this one here. F prime of x could be a big mess, isn't it? I'm going to have secant squared in the denominator. I'll just write it like this for the moment. And then secant of x times the derivative of the numerator. So that's going to be secant squared minus the derivative of the denominator, which is secant of x tangent of x times the numerator, which is tangent of x minus 1. Ugh. Looks like a big mess, doesn't it? Yeah, I don't see too much disagreement on that one. Let's see what we can do to clean this up a little bit. First things first, in the numerator, I'm going to write that as secant of x cubed, like that. And then in the denominator, this term has to multiply both of these terms. And I'm going to include that negative with it. So I'll get negative times tangent. It's going to give me negative secant of x times tangent squared of x. And then a minus times a minus gives me a plus. That's going to give me, let's see, it's going to give me a plus secant of x tangent of x over secant squared of x. Looks like a big mess. So right now we're just cleaning it up. Let me pause for a second. Make sure you're still with me. Did anything go a little too fast that you'd like explained a little bit more? Good on all that? Is there anything common in the numerator? Yeah, a secant. So let me take out a secant of x. And let's see what that leaves behind. That's going to leave behind a secant squared minus a tangent squared plus tangent of x. I still have my secant squared in the denominator. Yes, somebody's saying, can't we cancel? Yes, you can cancel one of the secants here with one of the secants here. And there's another nice little thing we can do here. I'll show you why later, but this simplifies pretty nicely. D'Angelo, you're giving me a knowing look, or is it a curiosity look?
Curiosity.
All right, this equals 1. So, wow, that's not too bad. I'll have to show you why later. All right, and I will. So that leaves me with 1 plus tangent of x divided by secant of x. So we've come a long ways in our simplification, haven't we? We did a lot. But I think we can go a little bit farther. Let's take a look at secant of x. Secant of x is really 1 over what function? Cosine of x. And tangent of x is really kind of the same thing, but I'll wait a step before I break that up a little bit. What happens when you divide by a fraction? What's our rule?
Multiply by the reciprocal.
Yeah, multiply by the reciprocal. So, okay, that's going to be cosine of x over 1, if you want, times 1 plus tangent of x. But tangent of x is what over what? Close.
Sine over cosine.
Sine of x over cosine of x. So when I distribute this, what happens? I get cosine of x, and then cosine times sine of x over cosine of x. What's going to happen with those cosines of x? Whew! Man, get out the oxygen bottle. That was tough. That was long. So what I want to show you next, and why I showed this one first, is the idea that you kind of get rewarded for thinking a little bit. And let's see if we can't do a little thinking on this one. First things first, are we okay with this, except for I got to go back and show you where you got this part from? All right, so no protests, or at least no loud protests. So let's take a look back at this problem and take it another way. So example E revisited. F of x is tangent of x minus 1 over secant of x. Instead of waiting till the very end to do all that monumental amount of simplification, let's do it up front. This is really sine of x over cosine of x minus 1 divided by 1 over cosine of x. And our trick just a minute ago was to invert and multiply. So that's cosine of x over 1 times sine of x over cosine of x minus 1. Blake. Where's Blake today? There we go. Thank you, Blake. What's going to happen when I distribute that, please?
We distribute cosine.
Okay, so what will I end up with?
You'll have sine over 1 minus cosine.
Nice. Does it look a little easier to differentiate this? Yeah, a lot easier to differentiate this, right? All right, so let's take a look here. F prime of x, well, derivative of sine is, come on, fill it in, cosine of x, minus derivative of cosine. What's the derivative of cosine?
Negative.
Negative sine of x, or cosine of x plus sine of x. Wow. On the test, you're free to do either one. I know which one I would choose, but you know, that's just me. You know, I can't say that I'm exactly like everyone else, so whatever works for you. But kind of the one message that I'm giving you to try and do it somewhat less subtly right now is that you're rewarded for thinking, okay? Where else did we see something like that? Well, when we're calculating the derivative of the cotangent, right? If you recognize that that's a cotangent, hey, the derivative is pretty easy. You could get it with the quotient rule, but I think I'd rather just say, all right, it's derivative of the cotangent. And we had a similar thing here. If we simplify this a little bit first, then the whole thing became a lot easier. So, I guess the message is fixed. It's you're rewarded for thinking. Okay, let's do a couple more. I'm going to skip down to example H and then example J to finish things up. I wouldn't mind doing example F, it's just I want to leave some time for some other things here. So, example H. This is a good one, and I like going over this one. You know what? Who was it earlier asking, can we use different variables? I think it was Antonio. In this case, I want to use a different variable because t's look too much like pluses. I'm just going to call that one h of x. It's rare that I'll use a t for this kind of stuff on exam. Cosine squared of x. Now, I love using this notation. It's very convenient, but it's also a little bit misleading too. What it really represents is cosine of x squared like that. And that's probably what you should do, at least early on, when you're working with these kinds of things and having to find a derivative. In our case, we want to find h prime of x. And well, what we have right now doesn't work. This is not a polynomial. You can't go 2 times cosine of x to the first power. It doesn't work, period. That kind of trick only works for polynomials. This isn't a polynomial. So what can I do? Well, it's kind of painful, but we can regard this as cosine of x times cosine of x. And if that's the case, what rule can I use now? Now I can use the product rule. Thank you. This is your f times g. So let's fill in the product rule. Thanks, Omar. So it's going to be f prime g plus g prime f. Nice. Max.
Yep.
What's f prime?
That could be negative sine x.
Yeah, negative sine of x times g, which is cosine of x. Good. And you should see something similar coming up again, right? It's going to be g prime times f, which is going to be negative sine of x times cosine of x. Now maybe you want to go and put parentheses around this or something like that. That's fine. But one thing I want to direct your attention to is that I've got 2 of these terms, right? They're both the same. So I'll just add them up. I have negative 2 sine of x cosine of x. And that's it. You're done. All right. But take a look. It does not work out to be, just 2 times this and subtract 1 from the exponent. It just doesn't work that way. There are things that we can do that we'll see in 3.3. Yes? I combine like terms. I've got one of these terms here and one of those terms there. So basically that gives me 2 of them, right? I got 2 of these terms. 2 of minus sine of x cosine of x. I'm just combining like terms. One of them here gives me 2. And then you multiply the 2 times the negative 1. Good? All right. Appreciate the question. All right, let's move on down to example J. Anything else on example H? All right. Example J, we've got f of x is 2e to the x cosine of x. And you're asked to find two things. Find f prime and f double prime. What do you think we're going to end up doing to find f double prime? Suppose you had f prime. What do you have to do to find f double prime?
Find that derivative.
Yeah, differentiate again. So you can differentiate the first time, and then take that and differentiate it to get the second one, f double prime. Nicole, I always miss seeing you because you're like right behind my screen here. So what rule do I have to use to differentiate this? Product rule. Nice. So I'm going to let that be my u, and that's going to be my v. Nice. So help me out if you would. What's the derivative of u, and what's the derivative of v? Charles, maybe you can help me out. What's u prime going to be?
Is it just 2EF?
Yeah. Nice. And v prime?
Negative sine of x?
Yeah, negative sine of x. Nice. So let's see if we can't figure out f prime of x. I'll give you a chance to figure that out. And then clean up your answer. Once you get your answer, clean it up. Is anyone else enjoying the snow? Cold?
No.
No? Got tired of that? It's only been, what, just over like 3.5 weeks since we had a day above freezing. It's not that long. Excellent, excellent, perfect. If you get the first one, clean it up, start working on the second one.
But you can't, I don't know, you're not adding those because they're not like terms. If this was a cosine of x, then you could get 4 to the x, etc. But you can do something here to kind of clean it up. It's in your best interest to clean it up. No, that's fine. That's perfect. I'm not sure if they're yeah, but it's negatives on the inside. It's not. I don't think it's.
Then I think it's minus 2x just take.
Oh, I see what you're saying. You're switching the order.
Yeah.
Okay. Yeah, you do yours in a different order, right? But yeah, it's gonna be the same thing. Okay. Yeah, exactly what you see. Yeah, so.
Okay. Looking good. Looking good. A lot of you are making good progress on this, and I'm very happy about that. So we want to do u prime v minus v prime u. Some of you are doing it in a different order, and that's fine. It happens every semester. You know, whatever works for you. U prime v plus v prime u. So u prime, actually I wrote that backwards, right? That should be u prime there, u prime there, u prime v. So it's going to be 2x, or 2e to the x times cosine of x, and then a minus v prime times u. So minus sine of x times 2e to the x. Now this has a common factor. These aren't like terms. I can't add them together like the previous one, but it has a common factor. That common factor is 2e to the x. So let me factor that out. If I factor that out, I get 2e to the x times, and I'm just going to use a bracket here, cosine of x minus sine of x. It's just for visual ease rather than anything else. So there's my derivative, and we cleaned it up. Are we okay with the first derivative? What's the benefit of cleaning it up in this case? It's actually really in your best interest to clean this one up. Why am I better differentiating this than this? Can anyone tell me?
Because you can do the product rule again.
We can do the product rule again, yeah?
Yeah, I was gonna say the same thing, 2e to the x would be the u, and cosine x minus sine x would be the v.
Nice. So right here, we can use the product rule again. It's this times this. But up here, do you know how many times would I have to use the product rule? I have to use it twice. I'd have to use it for this term and for this term. And that's starting to sound like it would really suck. So let's make our lives a little easier. Again, you're rewarded for thinking, all right? Don't just charge ahead with these things without thinking a little bit. All right, so let's work on f double prime. F double prime of x. So once again, you're going to have a u and a v. So we're going to have u prime v minus v prime u. U prime is just going to be 2e to the x again. 2e to the x times v, which is cosine of x minus sine of x, plus v prime times u. Plus v prime. Now let's see if we can't figure out what v prime is going to be. For v prime, I've got to differentiate both of these terms on the inside. What's the derivative of the cosine?
Negative sine x.
Thank you, gentlemen. Negative sine of x minus the derivative of the sine. Cosine of x times 2e to the x. Well, that wasn't so bad. Let's see if we can't clean this up a little bit more. I'm going to distribute the 2e to the x to these two terms. That's going to be a cosine of x minus 2e to the x sine of x. And then I'm going to distribute this to both of these terms, minus 2e to the x sine of x minus 2e to the x cosine of x. Huh. Okay. Does that help at all? Does that clean up in any nice way? Well, there are some like terms. Well, before we factor out, let's... Yeah. These terms cancel out completely, right? That one and that one, they're the same but opposite signs. So they cancel out to 0. How about the remaining two terms? Simon, what do we get for the remaining two terms? What happens there?
You can combine them to just be negative 4e to the x.
Exactly. These have the same, they're the same term, and we just add up the coefficients, so we end up with negative 4 e to the x sine of x, and we're done. Nice, very nice. Can't remember if I have this one graphed or not, so let's see. Yeah, here we go. So let me shut off this one. Let's turn on this one. Here's your graph, and let's kind of bring it into the fold a little bit. There we go. So when I look at the graph of the derivative, what should I see at the graph of the derivative at this point?
It crossed the x-axis.
Should cross the x-axis. There's another point where it should cross the x-axis. It's kind of hard to see, but right here should also cross the x-axis. So it should be positive, and then cross the x-axis here, and then it's negative until it crosses the x-axis here. Let's take a look at that one. Yeah, there you go. You know, kind of tough to see this one point here, but there it is. And there's our other point. So these places where you have a derivative of 0, our derivative function should cross the x-axis. And it should be increasing or decreasing in between. Likewise, you can shut off that graph and look at this one, play the same game. We should see the derivative here crossing the x-axis, and also here. So there you go. Crosses the x-axis at 0 and at pi. So looking good. Nice. Telling us exactly what we expected. Any last comments or thoughts on this one?
Is that supposed to be a minus or a plus for the constant for U1 or U prime? B?
Oh, it should be a plus.
Okay.
Thank you. Thank you. Thank you. Appreciate that. Bless you.
Bless you.
Anything else? All right. Good deal.